Welcome to this lecture on Bitcoin and blockchain technology. In 2008, a revolutionary concept was introduced to the world: Bitcoin. Its creator, operating under the pseudonym Satoshi Nakamoto, chose to remain anonymous, adding to the intrigue of this landmark innovation. Bitcoin represents the world's first successful decentralized digital currency, fundamentally changing how we think about trust and financial transactions. At the heart of Bitcoin's design is a technology called the blockchain, a distributed ledger that allows for secure, transparent, and tamper-resistant record-keeping without relying on any central authority. This concept has since extended far beyond digital currency, influencing modern finance, supply chain management, and digital systems of all kinds. By the end of this lecture, you will have a strong understanding of how Bitcoin works and why blockchain technology matters. Before Bitcoin, digital currencies faced a critical challenge known as the double spending problem. This issue asks, how do you ensure that a digital token cannot be spent more than once? In traditional financial systems, we rely on trusted intermediaries such as banks to verify transactions and maintain the integrity of currency. Bitcoin's genius lies in solving this problem without any intermediary at all. It introduced a decentralized consensus mechanism allowing transactions to be verified and recorded across a distributed network. No single institution controls the system, and yet the integrity of every transaction is guaranteed. This was a groundbreaking innovation with no precedent in the history of digital finance. To understand how Bitcoin works, we must first understand the basic architecture of a blockchain. A blockchain is a growing list of records, called blocks, linked together using cryptography. Each block contains three key components: a cryptographic hash of the previous block, a timestamp, and transaction data. The cryptographic hash acts as a digital fingerprint. Even the slightest change to a block's data produces a completely different hash, immediately alerting the network to tampering. Changing any one block would require recalculating every block that follows, a task that grows exponentially harder as the chain lengthens. This elegant design makes the blockchain a powerful foundation for secure and trustless record-keeping. The Bitcoin network is maintained by thousands of computers, known as nodes, each running the Bitcoin software and holding a full copy of the entire blockchain. These nodes are the backbone of the network's decentralized nature, independently verifying every transaction and ensuring the system operates without any central authority. When a transaction is made, it is broadcast across the network to all nodes. Specialized nodes called miners then group these transactions into blocks. Miners play a critical role in maintaining the security and continuity of the blockchain, as we will explore in the next scene. Mining is the process by which new transactions are added to the blockchain. It relies on a consensus mechanism called proof of work. Miners compete to solve complex mathematical puzzles, finding a number called a nonce that, when combined with the block's data, produces a hash below a required target difficulty. The first miner to solve the puzzle earns the right to add the new block to the blockchain and receives newly created bitcoins as a reward. Other nodes verify the solution, and if valid, the block is accepted and the process repeats. To maintain a consistent pace, the puzzle difficulty adjusts every 2016 blocks, approximately every 2 weeks, ensuring the average time between blocks remains around 10 minutes regardless of total network computing power. This self-regulating mechanism is central to Bitcoin's stability. Cryptography is the foundation on which Bitcoin is built. The most important cryptographic tool is the hash function. Bitcoin uses SHA-256, which takes any input and produces a fixed-size output that is practically impossible to reverse engineer. Even a tiny change to the input produces a completely different hash, making it a robust tool for ensuring data integrity. Equally important is public key cryptography. Every user has a public address derived from a public key, and a private key used to digitally sign transactions. This signature proves ownership without ever revealing the private key, maintaining both security and privacy. Together, these cryptographic tools ensure that Bitcoin transactions are authentic, secure, and verifiable by anyone on the network. While Bitcoin's scripting language is intentionally limited to ensure security and simplicity, later platforms have expanded these capabilities significantly. Ethereum introduced smart contracts, which are self-executing pieces of code stored on the blockchain that automatically enforce agreements when predetermined conditions are met. Smart contracts have opened entirely new possibilities. Decentralized finance allows users to access financial services without banks. Supply chain tracking ensures transparent and tamper-proof records of goods in transit. Voting systems and digital identity management become more secure and verifiable. These decentralized applications, known as DApps, represent a major evolution in what blockchain technology can achieve. Despite its revolutionary potential, blockchain technology faces several significant challenges. The most pressing is scalability. Bitcoin can currently process only around 7 transactions per second, compared to thousands for traditional payment systems like Visa. This has driven considerable research into improving transaction throughput without sacrificing security. The energy consumption of proof-of-work mining has also raised serious environmental concerns. Regulatory uncertainty persists as governments work out how to classify and govern digital assets. Privacy is another area of concern. Although Bitcoin transactions are pseudonymous, advanced blockchain analysis techniques can sometimes link transactions to real-world identities, posing challenges for users who value discretion. Researchers and developers are actively working to address these challenges. Proof of stake is a promising alternative to proof of work. Rather than competing to solve puzzles, validators in a proof-of-stake system are selected based on the number of coins they hold and are willing to stake as collateral, dramatically reducing energy consumption while maintaining security. Layer 2 solutions such as the Lightning Network enhance scalability by processing transactions off-chain and settling final balances on the main blockchain, enabling faster and cheaper transactions without altering Bitcoin's core protocol. In enterprise settings, permissioned blockchains allow trusted participants to operate in more controlled environments that prioritize performance and regulatory compliance, while still benefiting from blockchain's core strengths. Blockchain technology represents a fundamental shift in how trust can be established in digital systems. Whether through cryptocurrencies like Bitcoin, the implementation of smart contracts, or enterprise blockchain applications, understanding its 3 core pillars, distributed ledgers, consensus mechanisms, and cryptographic foundations, is essential for anyone navigating the digital future. Addressing the limitations around scalability, energy, regulation, and privacy will be crucial to ensuring this technology fulfills its promise of a more secure, efficient, and equitable digital world. Thank you, and we hope this lecture has given you a strong foundation in Bitcoin and blockchain technology.